Okay, we're recording. I'm going to share the screen now. Okay, you go. Today is Monday, the 18th of May, and it's going to be our third meeting on special relativity. And the day after tomorrow is the exam, it's the third exam. And then on Monday is going to be a holiday. And then we have two more meetings, two more class meetings, and finally, the last class meeting is going to be the final exam, which is on June 8th. June 8th. Okay. That's the situation here for the schedule. And now let's get to the notes. Insert page break May 18, 2026. 2026, that's a Monday. Today is right in here. The 15th week and the 26th meeting. 15th week, week number 15. Yeah, meeting number 26. So what did I do? It's okay. I corrected the report for the lab 4, for lab number 4, and uploaded the correction to your group folder. Okay. Okay. I'll be correcting. Okay, let's see. Exam 3 is the day after tomorrow. And the material is the following, right? Let me repeat here again. The material for the third exam is this one right here. Material for exam 3. Oops. Okay. Not good. It looks like I have to do all this dirty work here. All right. Material for exam 3. Material for exam 3. You go like that. Okay, plus labs 3 and 4. All this all this material, everything that's in boldface, right? Everything that's in boldface. Let's go back to our equation for time dilation. I want to emphasize that I'm using a notation different from the book. And there is also some vocabulary that we have to be aware of, right? Here you go, my notation. And the book's notation. Okay, my notation, right? So here you go. C refers to the clock that is at rest with respect to referential B. Okay, and that's the period of the clock, by the way. That's the period of the clock, the time it takes for photon to complete a full oscillation. The light clock, right? Here you go. I put VBA. The book uses the V notation. And this delta T naught, okay, as well is the same as TCB. Delta T is a TCA. Okay? Delta T naught is also referred as delta T naught is also referred as proper time. Okay? Because it's it refers to the clock that is at rest. Proper time because it refers to the clock that is at rest with respect to a given referential. And so let's get that here. It's a very good notation. I like it, this name that they gave, right? I think it's very appropriate. And what's that? Okay, here you go. Light clock, right? Here you go. Here, this clock that you see right in here is measures the proper time because the clock is at rest with respect to referential A. Okay? And this clock here in red also measures the proper time of referential B, right? It's not the proper time in referential A, but it's the proper time in referential B because it is at rest with respect to referential B. And like before, this clock here in black is the proper time of referential A. That's the important definition that you gotta know, that you have to know, right? And remember that we have this term here that already plotted for you, right? 1 divided by that. And I plotted that for you. Here you go. Let's take a look. That's how it looks like. That's how it looks like that 1 minus v squared over c squared, square root, right? 1 divided by that, by the square root. And note see that it goes asymptotically at the speed of the light. So when the velocity is equal to c, okay, we have a division by 0. We have a delta t that's very large, so it goes to asymptotically to infinity. Okay, but notice that for most, okay, for most speeds, don't forget, this here is the ratio, right, of the velocity with respect to the speed of the light. Here is 20% the speed of the light. Here is 40% the speed of the light. Here is 60% of the speed of the light. For most of this graph, the effect is very small. We don't feel much of a relativistic effect all the way up to, let's say, 60% of the speed of the light. And the effect start to become more measurable at higher speeds, 80% the speed of the light. Okay, so let's take a look here. We're gonna go into access option. Let's see how I'm gonna do that. I'm going to, okay, I'm gonna do this following. I'm gonna do like that. 3.5. 3.5. So you can have a better measure. And I'm going to increase the numbers. One decimal place, increase the decimal places. Okay, so, oh, even better, we can look at those numbers right in here, right? So here you go. Instead of looking at the graph, let's look at the actual number, so you can have a better idea how those numbers work, right? So all the way up to, let's say, to 40% the speed of the light, we get just a 10% difference in the period of the clock. Okay, all the way up to 40, 45% the speed of the light. And then things just keep increasing, okay, until you get a 600% increase. That would be 600% increase, okay, at 99% the speed of the light. So keep that in mind. We don't see those relativistic effects in our day-to-day life because you require to be moving very fast. You require to be moving at 40% of the speed of the light, 45% the speed of the light. That's why it took us so long for us to figure that out, right? That's why it took us so long to figure that out, the theory of relativity, because it requires speeds that are very large. And this type of speeds can also be witnessed doing experiments doing quantum mechanical experiments. You can measure these effects, these relativistic effects, with subatomic particles that can travel very fast. And that's where the evidence start to be uncovered in the experiments that we perform with particles at the quantum realm. Keep that in mind. Good. Okay, delta t naught is also referred as the proper time. The proper time. And let's not forget that this ratio is always, the ratio gamma, right, is always greater than 1. The ratio is always greater than 1. And now what we're going to do, we're going to talk about let me give you another example of the type of speeds that we are used. The fastest macroscopic object launched by humankind is this NASA's Parker Solar Probe. NASA's Parker Solar Probe. Let's take a look at the NASA Parker Solar Probe. NASA's Parker Solar Probe. Parker Solar, here we go. A mission to touch the sun, the surface of the sun. The first spacecraft to fly through the corona, the sun's upper atmosphere, in 2021, with every orbit bring it closer. The probe faces brutal heat and radiation to provide humanity with unprecedented observations, visiting the only star we can study up close. Let's take a look here. Okay, this is the spacecraft. Okay, and what's it? Let's take a look here. Fastest. Fastest spacecraft launched by mankind. Yeah, Parker Solar Probe. During its closest approach to the sun, the spacecraft reaches a staggering top speed of 430,000 miles per hour, and 24 times faster than the International Space Station, 200 times faster than a high-powered rifle bullet. Fast enough to travel to New York to Los Angeles in 20 seconds. I want to change that to kilometers per second, right? Let's take a look at 687,000 kilometers per second is what? 687,000 kilometers per second. I want to kilometers per hour. Oops. Kilometers per hour. I want kilometers per second. What I have to do is to divide this value here by 3,600. This one divided by 3,600. 190 kilometers per second. Now we gotta find out which is that the speed with respect to the sun or is the speed with respect to the Earth, right? They didn't mention here. Is that a relative speed with respect to the Earth? Is the relative speed with respect to the sun or some other relative speeds, right? Let me ask, is this speed relative to the sun or relative? Is this speed relative to the sun or to the Earth? Let's see if he reply, because you didn't specify. Yeah, is the speed, okay, is the speed of NASA's Parker Solar Probe relative to the sun or to the Earth? The speed of NASA's Parker Solar Probe is calculated and set relative to the sun. Okay, makes sense, right? That's the heliocentric speed. It makes sense. So it's orbiting the sun, and that's 190 kilometers per second. Some time ago, I remember when I used to receive the bulletins from the Voyager, from NASA, right? From the relating the health of the Voyager spacecraft. I remember that they cited that the speed of the Voyager spacecraft at a certain point was at 100 kilometers per second. So the NASA Parker Solar Probe is almost twice that of Voyager. And we can even calculate what's the effect right? What's the effect of what's the relativistic effect at the highest speed? It's possible to do that. Okay, at this highest speed of a macroscopic object. Okay, so here go V divided by C. I'm going to divide my 190 kilometers per second by 300,123,000 kilometers per second. It's very small. It is less than a tenth of a percent. It's less than a tenth of a percent. And let's calculate the amount, right? Here you go. I can use exactly this equation here. I'm going to use it right in here. Right in here. There you go. Oops, almost one. Almost one, right? The speed is so small that we have to put some decimal places in there to see if we can get anything. Oh, yeah, here you go. Look here, the period, right? The period of a light clock in that spacecraft. The difference of the period is going to be very small compared to the period of a clock that stays here on Earth. Okay, it's my goodness, it's so difficult. It's so difficult to even visualize this number, right? Let me get that. I'm going to paste it right in here. Yeah, here you go. Let's see here. 1, 2, 3, 4, 5, 6, 7. Okay. 2 times 10 to minus 7. 2 times 10 to minus 7. Okay. So even for the fastest macroscopic object that mankind has launched, the time dilation effect is very small, very difficult to be measured. Okay, having said that, now we can start talking about the phenomenon of length contraction. Okay, we can now talk about length contraction, but just remember, right? The period of a light clock is a function of the velocity of that clock. Is a function of the velocity of that clock. And we can also say that the length of an object is also going to be a function of the velocity of your ruler, for instance, of your ruler. Okay, so here you go. Length of the ruler with respect to referential A is going to be a function of the velocity of the ruler with respect to the referential A, which ends up being equal to the velocity of referential B with respect to A, okay? So 2 different referentials. The ruler is placed in referential B, is at rest with respect to referential B, okay? And it's going to be, and the length again is going to be a function of the velocity. And by the way, what we get is a contraction in the length. How do we calculate that, right? How do we prove that, right? How do we prove that? Okay, so the way we do, we come up with a thought experiment. Let's come up with a thought experiment. What's going on here? Oh my goodness. I am pasting it in the wrong place. Just notice that. Yeah. Okay, let me. Yeah. Okay. Insert page break. Here you go. Better place to keep it. Okay. In order to derive the length contraction, comma, we must come up with a thought experiment. And by the way, that's something that Einstein used to do, okay? To visualize his complicated, the complicated effects. Okay, and consider two planets separated by a distance L. Consider two planets separated by a distance L. And a spaceship moving at a relativistic speed greater than 40% the speed of the light. The spaceship is flying from the first planet to the second one. For you who stayed behind, you measure the time the trip took us being, right? For you who stayed on Earth, in one of the planets. And by the way, I am assuming that the other planet is at rest with respect to the first planet. Or let's say the speed is negligible, right? The relative speed of those two planets is negligible relativistically speaking. And this guy can time how long the spaceship is going to take to get to the other planet, right? How do you do that? You get the speed of the spaceship, get the length divided by delta t. And that's a straightforward calculation. No need to do any relativistic effects, right? Because you are in a planet that is at rest with respect to the other planet that the spaceship is going to. Okay, so that L divided by V is going to be how much time the observer would measure, observer on Earth would measure for the spaceship to get to the other planet. This delta T is how long an observer. Consider two planets. Let's see, planet A and planet B. Planet A and planet B. Here you go. Separated by distance L in a spaceship moving at relativistic speed. This spaceship is flying by planet A. It's flying by the consider two planets. Planet A separated by distance L and spaceship moving at relativistic speed V, comma, passing through planet A and moving towards planet B. Okay, that's better now. For you who stayed behind in planet A, in planet, let's see, consider two planets. Consider two planets having relative speeds, right? That are negligible. that are negligible. Let's put it this way too. Negligible. Two planets are separated by distance L, and a spaceship these two planets, let's put it this way. These two planets are separated. A spaceship moving at a relativistic speed v is passing by planet A and moving towards planet B. For you who stayed behind in planet A, you are you are in planet A. Here you go. You are in planet A, and you measure the time it took for the spaceship to reach planet B. Like that. Spaceship length divided by delta t. You know the speed of the ship, right? Consider two planets. These two planets are a spaceship. Okay, moving at relativistic speed v. That's how long you're going to measure. For you who is in that planet A, okay? This delta t, don't forget, this delta t is how long an observer in planet A measures the time of travel. The time of travel, right? However, for the astronauts, this is the moving referential that is inside the spaceship. Inside the spaceship. However, the astronaut that's inside the spaceship determines a different period for the strip given by, it's going to be given by, here you go. Don't forget proper time, right? It's going to be given by that. Okay, that will be the proper time, right? So the astronaut must measure a shorter time. And by the way, it's like that. Because the time is going to be shorter and the speed is going to be the same, the astronaut inside the spaceship is going to see a shorter distance. That's why I put L prime here. Okay? The speed is going to be the same. It's not going to be different. So now we can solve this equation for L prime. Like that. On the left side of the equation, delta T prime. And what else can I do? I can use this relationship that you see right in here, right? Why do I do that? I do that to cancel out the V, okay? So you're going to see it's going to become a much more convenient relation. I'm going to substitute delta T for L divided by V. And let's not forget, this is the distance the astronaut in the moving spaceship measures between planet A and B, okay? Here you go. Just to clarify, repeating, right? Repeating here. I'm gonna repeating here. L prime is the distance that the astronaut measures from planet A to planet B. L is the distance, an observer in planet A measures from A to B. Okay. And now let's proceed. Let's proceed here. V is going to cancel out. V here is going to cancel out on both sides. And now we're getting to the point where we like that. That's what the distance between planet A and planet B as measured by the moving referential of the astronauts. Since this number is less than 1, since the number inside the square root is less than 1, the distance that the astronaut measures from A to B is shorter than the term length contraction. Okay. So another way of expressing this L prime is in terms of gamma, right? 1 divided by the square root is gamma. Consequently, L prime is L over gamma. And L prime is less than L. We proved length contraction, right? We proved length contraction by using the result of time dilation. And we proved time dilation using the light clock. Notation of the book, right? Let's compare the notation of the book with my notation. I prefer my notation, okay, because it doesn't eliminate important information. My notation, right? Okay, the distance from planet A to planet B as measured, L sub A is the distance from planet A to planet B, right? As measured by referential A. Let's see, I'm going to, that's an unfortunate notation here. I don't like that. Let's put, instead of B, let's put S. S for the spaceship, right? S for the spaceship. Yeah, that's a better, okay? L sub A. L sub A is the distance that an observer in planet A measures from planet A measures from planet A to planet B. L sub B L sub B is the distance that an observer in spaceship S, no, it's not L sub B, right? L sub S. L sub S is the distance that an observer in the spaceship S measures from planet A to planet B. Okay, V sub S uh, ooh, V sub S is V sub S with respect to A, right? I'm gonna put here with respect to A is the speed of spacecraft S with respect to planet A. That's how you should read this notation. Velocity of spacecraft S with respect to A. And here you go, we have the factor gamma again, right, which appears rather, that occurs with loss of frequency. The picture that you have to have in your mind is this one right here. I should have presented that picture for you before, right? Here you go, here's the rocket, right, the spaceship. The referential B. I call it this planet D. Oh gosh. I'm not gonna fix that. Now I have to fix everything, right? Jesus Christ. What should I do? Yeah, I call it Planet D. Let's see if I can fix everything. It's gonna take a long time to fix that. This delta T is how long I'm observing planet A. Let's see, consider two planets, planet A and planet D, okay? Having relative speeds that are negligible, okay? V of D with respect to A is approximately zero, okay? Approximately zero. Here you go. These two planets separated by a distance L, a spaceship moving at a relativistic speed V greater than 40% the speed of the light is passing by planet A and moving towards planet D. You are in planet A and you measure the time it took for the spaceship to reach planet B, planet D. That's how long it takes for, according to your referential, right? L divided by V. This delta T is how long an observing planet A measures the time of travel. However, the astronaut that's inside the spaceship determines a different period for the trip. Determines a different amount of time that this trip takes, that this trip took. Or delta T prime is shorter, right? Is 1 over gamma. And then delta T prime is also equal to the distance that the astronaut sees between planets A and D divided by V, right? Repeating here, L prime is the planet D. L is the distance an observer in planet A measures from A to D. Here you go. Since the number inside the square root is less than 1, the distance that the astronaut measures from A to D is shorter than the term length contraction. Okay, so now my notation, right? The distance between planet A and B, distance as seen from referential B, right? And the velocity of B with respect to A. And here you go. Now LA is the distance that an observer in planet A measures from planet A to B. L sub B is the distance that an observer in the spaceship measure from planet A to planet D, right? You gotta fix it, fix it. VB of A is the speed of the spacecraft with respect to planet A. And now we have the actual drawing. Okay, and we can now document what we did so far. Events and inertial referential, the postulates of relativity, time dilation, length contraction. We did length contraction. Okay. So we already saw what happens to time and length when they are measured from different referential. Right? So the question is, what happens to linear momentum? Now let's see what happens to linear momentum. Okay, and if you want to understand it better, I highly recommend you to look at the mechanical universe episodes 42, 43, and 44, okay? To understand better, okay? Better relativity. Take a look at episodes 42, 43, and 44 on relativity of the mechanical universe, Okay? Here is the links. I highly recommend you take a look at that. It's really nice the way they did it. Okay, the first time I saw it, this series, okay, I was impressed that I really grasped it, how relativity really works, okay? So here go, here's the character. Okay, here you go.
And Henry.
No, here you go. Here's the moving referential, right? Lawrence, this guy is Lawrence. And you have Einstein in the other referential. In this situation, Einstein is at rest with respect to us, and Henry is moving with respect to us. In the previous screen, right?
The train speed seems to be 0, and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. But Lorentz said that perceptions of light waves would be radically different. He suggested that even someone traveling at nearly the speed of light would still observe light moving at 300,000 kilometers per second. How could that be? Consider two observers in...
Gotta go faster than that. Here you go. Okay, now I can slow down. Here you go.
And Henry.
Here in this case, you know, the Henry's referential is at rest with respect to us, right?
Just for the sake of argument.
Now he switches. He made Einstein's referential at rest with respect to us.
Okay? They observe a flash of light.
And look what happens.
A sphere of light expands.
Flash of light.
Since each measures the speed of light relative to himself, and each believes correctly that he is always at the center of that expanding sphere.
So that's what Henry saw for the flash of light. That is
even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at 2 different times.
That's a very good way of visualizing events that are simultaneous in one referential. Events are not necessarily simultaneous in the other referential. Okay, that's one of those funny consequences of special relativity. But take a look at those 3 episodes during your there at home, right? When you're not doing anything, it's really, gives a much better grasp of special relativity. Now, let's talk about relativistic momentum, okay? How do we formulate the relativistic momentum, okay? From physics 7, we have that the regular or Newtonian momentum is given by, is a vector, right? Newtonian momentum, Newtonian linear momentum, mass times velocity. If the net force applied to an object is 0, then this momentum is conserved. Initial momentum is equal to final momentum. Okay, so here you go. That's what we learned before, right? If net force applied to an object, the initial momentum must be equal to final momentum. And that comes from Newton's second law of motion, right? That is consequence of, which is consequence of Newton's second law of motion. Net force is mass times acceleration. But acceleration can also be rewritten as delta v over delta t, right? Delta v over delta t can be rewritten as v minus v naught over delta t. Right? And by the way, which can be rewritten as mv minus mv naught, right? Here you go. Which can be rewritten as p minus p naught. P minus p, oh gosh, minus p naught. Here you go. If net force is equal to 0, then we have conservation, right? We have conservation of linear momentum. If net force is equal to 0, then we have conservation of linear momentum according to Newtonian mechanics. According to Newtonian mechanics. Okay. Like that. Okay. So the question is that came to Einstein, right? How can we have conservation of relativistic Linear momentum, right? Linear momentum, right? How can we have conservation of linear momentum in relativity? How can we have conservation of linear momentum in relativity, right? Linear momentum in relativity. Oh gosh, in relativity. So Einstein sought and sought and sought, and then he discovered the following. Okay, if linear momentum is to be conserved in relativity in both referentials, right? A and B, we must redefine linear momentum. Think about that. We are talking about linear momentum to be conserved in both referentials A and B. Okay? And so we have to redefine linear momentum. You already know that linear momentum is, let's get that here. Here you go. You know that Newtonian linear momentum is given by that, right? And I'm going to drop the Newtonian subscript. So in order to have conservation of linear momentum in both referentials A and B simultaneously, and in relativity as well, the relativistic linear momentum must be rewritten as gamma times m times v. Okay? And we can rewrite it again. Okay, it's going to be like that. Like that. We can rewrite this equation in a different way. I'm going to take out the v here, the v vector, and look what we have. We have the term, this term that you see here, okay, the term in boldface, the term in boldface is also referred to as the relativistic mass. Relativistic mass. Okay, so if we use the above relation for the linear momentum, if you use the above relation for the relativistic linear momentum, whenever the net force applied for an object is 0, 1, the numerical value of relativistic momentum measured with respect to referential A is still different from the numeric value when measured in referential B. However, okay, why is this thing? Okay, here you go. However, for this specific relation, the relativistic momentum is conserved in both referential A and B. The numerical values may be different, but they are conserved. Okay? In other words, the numerical value may be different. However, they are both conserved before and after a given collision. Keep that in mind. And I'm going to put that according to my notation, right? Here you go. Net force applied to a particle, to an object P, right? Net force applied to an object P is zero. If net force applied to an object P, to a particle P, is zero, then we do have that the initial linear momentum according to referential A is going to be equal to the final linear momentum as measured by referential B. And, okay, and I'm just repeating, right, what I said before. I'm repeating in mathematical terms. The initial momentum, linear momentum, according to referential B, is going to be equal to the final linear momentum according to referential B. Okay? However, don't forget, however, initial momentum as measured by A is not necessarily equal to initial momentum as measured by referential B. Okay? And here is, linear momentum of the particle P, right? Particle P, here you go, is equal to gamma mv. Particle P with respect to A, referential A, is equal to V of P with respect to A. That's the notation I'm using here. The term in the Bose space usually referred as the relativistic mass, implying that the mass as measured by observer in referential A increases as the speed of P increases. I want to take a break right now. It is 10:50. 10:50 a.m. To 11:05, right? 05 a.m. break. Do you have any questions? Okay, so let's take a break now, and I'll be back in 15 minutes. I am back here. I'm sharing the screen, and so let's summarize the surprising results from relativity. That we have obtained so far, right? Here you go. Surprising results from relativity. The first one, speed of the light is the same in any inertial frame of reference. Whether the referential is at rest with respect to a light source, moving towards or away from it, the speed of the light that you measure in these three different referentials will always be the same, 300,000 kilometers per second. This is one of the postulates of relativity. And this postulate of relativity gives rise to other consequences that are surprising, right? Two identical clocks, one at rest with respect to you, and the other moving at constant speed. That would be the clock in referential B. The clock at rest with respect to you in referential A is clock C prime. I don't like this notation. let me put, okay, the clock at rest with respect to you in referential A is clock C, okay? The clock moving with respect to you in referential B is clock C prime. I prefer like that. Using the postulate, the above postulated relativity, we find that T C prime A, let me see here. Oh yeah, okay. Yeah, yeah, is greater than T C prime B. That's what we call time dilation. Remember, C prime is not the clock, it's the clock that is in referential B, right? That's what C prime is. In other words, the period of the other clock depends on the relative velocity. This is the phenomenon of time dilation. This is the phenomenon of time dilation. Another important result is that events that are simultaneous in one referential are not simultaneous in another referential. However, keep in mind that for something like that to be measurable, one referential must be traveling at relativistic speeds. Whether an event is simultaneous or not, it depends on the relative velocity. Relative velocity. Length contraction. A spaceship moving past you at a relativistic speed, at a relativistic speed seems is measured to have a shorter length. But very important is the length in the direction of the velocity vector, okay? Of the velocity vector, by the way. Okay, so here you go. However, an astronaut inside the spaceship measures a length L. In other words, the length depends on the relative velocity. The length measured, the length of anything, right? Measured at another differential depends on the relative velocity of the referentials. Okay, and finally, what we just saw, differentials cannot be plural, right? Here you go. Let's see. That's the word referential has a plural. That's the word referential has a plural, the plural form, okay? No, the word referential does not have a plural form. It's primarily an adjective, okay. Okay, so last one. Relativistic mass increases with velocity, whereas the mass in Newtonian mechanics does not change. In other words, the mass depends on the relative velocity of the particle flying by you. However, someone else moving side by side this mass with zero relative velocity, we measure a mass that coincides with the rest mass value. 5 different A, B, C, D, right? 5 different surprising results. The very first surprising result is one of Einstein's postulates, and everything else that follows here depends on that Einstein postulate. And we covered one more section of relativity, which is relativistic momentum. Okay, so what you have now, let's talk about the equivalence of mass and energy. Okay, in Newtonian mechanics, mass and energy are concepts completely independent of each other. Okay, in Newtonian mechanics, object with mass and concept that has no mass whatsoever, such as energy and the photon, right? Such as energy and the photon of light are independent from each other. A mass may have some energy, like kinetic or potential, and this energy does not add any mass to the object. That's still in Newtonian mechanics. Furthermore, there is no relation between them. That's not so in relativity, in special relativity. Einstein found that a mass at rest has energy that can be tapped from. And the equation that he found it out, right, is one of the most famous equations of his. It's not a postulate, but it is a consequence of his postulates. Here you go. A mass at rest has some energy. That's the rest means energy, which is equal to mc squared. Okay, and don't forget, folks, this is a huge amount of energy, because we are getting a big number, which is 300,000 kilometers per second, and we were squaring it. Okay, what you see here is a huge amount of energy, because we have the rest mass multiplied by the square of the speed of the light, right? Which is already a very high value. This is the whole principle of the atomic nuclear energy and nuclear bombs, right? This is the whole principle of the nuclear bombs. Atomic energy refers to the splitting of the nucleus of an atom. Fission energy. Nuclear energy refers to the fusion of two different nuclei, also referred as nuclear fusion. Notice the difference between nuclear fission and nuclear fusion. The first is atomic energy. The second is referred as nuclear energy, right? Fission and fusion. Okay, fission means splitting, right? Fission means splitting of the atom. Fusion means exactly what the word states, right? The bringing together of two different atoms. Even better would be like nuclei would be better. Okay, but how Einstein derived the above equation? Okay, we're not going to derive it here. It requires some calculus, but I can give you the step-by-step procedure. Okay, we start with the work done by the net force. Okay. Step-by-step procedure is the following. Using the definition of work done by the net force. They call the work kinetic energy theorem, right? Work kinetic energy theorem. Work done by the net force is the net force multiplied by delta x, which is the difference in kinetic energy. Final kinetic energy minus initial kinetic energy. Next, what do we do next? In the above relation, you use the relativistic momentum for the net force. This one goes soon after that. Good. In the above equation, you use the relativistic momentum for the net force. Okay, so we go net force. I'm gonna put it oh. Okay, delta P over delta T. Net force, right? The delta P over delta T is the net force. But because we're doing the work done by the net force, we still have to multiply it by delta x. And let's not forget, right? The work done by the net force is also equal to the change in kinetic energy after some higher level derivations that requires differential and integral calculus. We end up with the following formula for the relativistic energy. Go. Do you see the factor gamma appearing again? Relativity. Okay, gamma mc squared. If the mass is at rest, this term disappears, right? And we end up with mc squared. Gamma is going to be 1, and you end up with mc squared. Okay. Once the mass is at rest, you go E naught refers to the rest mass. I don't need that anymore. What is the rest energy of 1 kilogram mass? This is a very good exercise to do it. Okay? You can come up with a, well, I got, you can calculate it. Here you go, let's see. 1 kilogram mass, right? Let me get here. Oops. Mass, kilogram. 1 kilogram, not grams. And energy, rest energy. Okay, and then we can come up here and multiply that by c squared, right? Don't forget, it should be in meters per second, not in kilometers per second. So here you go, 300,000 kilometers per second, 300 million meters per second. And we still have to raise to the second power. Okay, so here you go. That's the number that I'm getting. 9 times 10 to the 16 joules. Okay, that's what the number we get. So that's the rest energy of 1 kilogram mass. Now let's see what this number is. A very large number, right? What does it mean? What does it mean, right? We have to visualize what this type of energy is all about. Let's try to make sense of this large number. Doesn't make any sense to come up with this large number if you cannot compare it. If you cannot say what we can do with this large number, right? How many houses, for instance, can we power in a given month? In a given month with this amount of energy. Okay? Assume that an average house spends roughly 400 kilowatt hour per month of energy. You can also look at your electricity bill to find out how much energy you spend on the average. Okay, so that's a very good way of finding out what this number is all about, right? How many houses can we power in a single month with this amount of energy? And don't forget, joules is just one way of measuring energy, and kilowatt hour too is just another way of measuring energy. There is a conversion factor, by the way. And here you go, solution. We can, okay, a single house spends 400, here you go, rule of 3, right? A single house spends 400 kilowatt hour in a single month, whereas X houses spend that much energy in a given month. That's how we come up with a solution, right? And we have to convert kilowatt hour in joules. Months cancel out, right? This month here cancel out. Kilo is 1,000. So you can, and watts is joules per second. Joules per second. And 1 hour is 3,600 seconds. That's how we do the conversion from kilowatt hour to joules. Second cancels out with seconds, right? You go, seconds cancel out with seconds. Joules cancel out with joules. 10 to the cube. And we gotta solve for X. X is the number of houses that we power in a single month. 9 times 10 to the 16 divided by 400 times 1,000 times 3,600. Let's see what we get. I'm gonna get here gonna be 10 to the 5th, right? And then we still have another 3 orders of magnitude, so 10 to the 8th. You gotta do this math. Let's put a multiplication sign here. Like that. And 9 divided by 4 divided by 3.6. And what I get? I get 0.625, like that. Okay. Those powers, they are going to cancel out, right? And we still get lots of houses. And 10 to the 16 becomes 10 to the 8. So we are talking about millions of houses, okay? We're talking about 0.625 times, yeah, 62 million and a half, 62 million and 500,000 houses. For an average of 4 people to house, let's see, 250 million people. So it's a country like the size of Brazil, okay? Brazil has a population of 250 million people, which is comparable to the population of the United States, which is around 300 million people. So with a single kilogram, you can power the houses of 250 million people in a single month. That's how much power you get from a single kilogram mass. Did I do the calculation right? Let's see if I did the calculation correctly. Yeah, okay, yeah, I did it correctly. 62,500,000 houses. Okay. For assume 4 people inhabiting a single house, and we get 250 million person. Okay, which is the equivalent of powering in 1 month one of the most populated country in the world. Okay. In the world, which is Brazil. Brazil has 250 million people. And Brazil is a very large country, the size of almost the size of the United States. Okay. So when scientists look at these results obtained by Einstein, right, they realized that they could tap into this energy, a huge amount of energy. They realized they could, when scientists look at this result obtained by Einstein, they realized that they could tap into this huge amount of energy to either power an entire country or create weapons of immense destructive power than the atom bomb and the hydrogen bomb. In the case of nuclear fission, a single atomic nuclei nucleus is split into two. In the case of nuclear fission, two atomic nuclei are combined into a single one. They fuse with each other, right? Now that if you memorize the energy of a rest mass, right? It's not going to be difficult to memorize the relativistic energy of a moving mass. The relativistic energy of a moving mass is just the factor gamma multiplied by the rest energy. Right in here. It's not difficult to memorize, right? Just memorize mc squared, and you get that the relativistic energy of a moving mass is going to be gamma times m times c squared. Okay? I think I'm going to get another break right now. Yeah, let's go for another break a little bit earlier, right? Let's have our break a little bit earlier now. And break from 11:35 a.m. to 11:50 a.m. Okay. And I see you in 15 minutes. I am back here. And okay, so we got the relativistic. We got what we have so far, right? We got the following equations. One, relativistic equation for relativistic momentum. For the relativistic momentum, we got rest mass energy. We got the equation for the relativistic energy, not at rest, mass moving mass, right? Relativistic energy for a moving mass, or a moving mass. That's what we got. Oh, there's more, right? Length today, just for today, right? Equation for length contraction, equation for relativistic momentum, for the rest mass energy, and relativistic energy. And what else can we get it here? You know, what else can we come up with? Okay, we'll now derive an equation for the relativistic kinetic energy. Okay? Assuming there is that the mass has no potential energy whatsoever. Okay? Assuming that the mass has no potential energy whatsoever. And the way it goes is like that, you know? Since there is no potential energy, right? We can say that the kinetic energy, the relativistic kinetic energy, is the relativistic energy minus the relativistic rest energy. And then in the next step, we use our equations that we found out before, right? Gamma, mc squared, and we get mc squared as well, right in here. And we can put mc squared in evidence. We can go further than that too. We can spell out what gamma is. Gamma is 1 divided by square root of v square, 1 minus v square over c square. That's the velocity of the mass, right? Is there anything else that we can do? I don't think so. Okay. So that's what the kinetic energy is all about. Okay, that's exact. Okay, the above is the exact equation for the relativistic kinetic energy. Now let's do something else now. We are now going to find an approximation for the above equation in powers of V over C. Okay, we can do that. V over C is always, notice the V over C is always less than 1, right? Less than 1 and greater than 0. Greater or equal than 0, you can say like that. V over C less than 1, greater or equal than 0. So consequently, this term here is like a x such that x is less than 1. And because of that, we can expand this term that you see right in here in terms of powers of V over C. Okay? It's possible to do that. You expanding The gamma term in terms of powers of V over C, we get what? You go, I'm gonna expand this one here, right? This term right here, which by the way, can be written down in terms of a negative power, negative half power. When we do that, we're gonna get an interesting result as well. Here you go. We're expanding in powers of V over C. You get something like that. Okay? Minus half. This minus half comes from here. We get minus V squared over C squared, which comes from here. First power. Then we get another term, 3/8. That comes also from here. Okay? And then we have a V over C squared to the second power. V squared over C squared to the second power, and so on. Up to the first order approximation, okay? Up to the first order approximation. First order approximation will be all the way up to here, okay? That will be second order approximation. And the other one will be third order approximation, fourth order approximation, and so on, okay? So up to the first order approximation in V squared over C squared, we get something like that. Notice that now we have an approximation. Here we do not have approximation, we have an equality sign. Okay, and we are going to do a next step. Here go this negative sign, cancel out with the other negative sign. The V squared over C squared remains. Half remains. Here you go. And now I can replace this relationship right in here for the equation for the kinetic energy. Let's get that. Let's fish it. Okay, that's the equation for the kinetic energy right in here. And now we can, instead of having an equality, we are going to have an approximation sign. Approximately. Why is that? Because I am going to substitute this approximation right in here. Okay? Next step, 1. Cancel with this other one. And then we are left only with this term right in here. Notice that the C squared is going to cancel out with C squared, right? And let's see, C squared cancel out with C squared. And look what we get. We get exactly that expression for the Newtonian kinetic energy, which is nothing but an approximation to the relativistic kinetic energy. Okay? These results that you see right here give us confidence that we didn't do any We didn't do any mistakes in our derivation. Give us this type of confidence. But then we can go another step. Okay? I got the approximation to first order for the kinetic energy, and we got the result for the Newton's kinetic energy. But now I can come up with another approximation. We can come up with the second order approximation here and see how the kinetic energy, the kinetic relativistic energy, looks like. Okay? How does the, here you go, how does the kinetic energy and the relativistic, the equation, how does the equation for the relativistic kinetic energy looks like? For up to a second order approximation, right? So we're going to use that approximation that you saw. Here you go. Here you go. That's the one. We're going to use this equation, which is the exact value for the kinetic energy. And we are going to look for this other equation right here. Okay, so this negative sign, right? Cancel out with this negative sign. I don't need the power, the first power there. I'll multiply by half. This positive sign multiply this negative sign that you see right in here. And now v squared to c squared becomes v to the fourth power divided by c to the fourth power. And that's the second order approximation. You have other terms there, third order approximation, fourth order approximation, okay? All those third, fourth, fifth order approximation has a power of 3, power of 4, power of 5, and so on, okay? Because I have these ellipses right in here, I can keep my equality sign. But once I drop the ellipses in the equation, I have to substitute this equality by an approximation. And now we substitute that right in here. Let's see how it looks like. And don't forget, we are going to have an approximation here now. All that stuff. We already know that one is going to disappear, right? Because of the previous result, 1 minus 1 disappear. Here's my first order approximation. Here's going to be my second order approximation. Let's see if I can. Oh, yeah, I can put v squared over c squared in evidence, right? Here you go. Yeah, I can put the half as well in evidence. Here you go. Can put the half as well in evidence. You go. And when I put the half in evidence, 8 becomes 4. V to the fourth power over C to the fourth power becomes V squared over C squared. Okay, like that. And the C squared still can cancel out. Like that. Oh, I'm going to put my M next to V squared. Remind you that this guy is a kinetic energy. Okay, that's my second order approximation for the kinetic energy. Second order approximation for the relativistic kinetic energy. This approximation is good up to 10% of that, right? Yeah, up to 10% of that. Let's see. Is a good approximation for V squared over C squared less than 0.1. Okay? V squared over, let's see, represents square root. Yeah, so we are talking about this approximation is good up to 31% of the speed of the light. Okay? So which should be V over C approximately, you know, V over C, 31% of the speed of the light. Around that, 32. You incur in an error of less than 10%. I actually incur in an error, yeah, that's right, less than 10%. That's my second order approximation. And so just remember, right? Newtonian mechanics is just an approximation to Einstein's theory of special relativity. And now we can come up with the rest. Okay, so what I want to do now is one more topic on special relativity. And that's going to be relative motion. We have time. Okay, that's good. We have plenty of time here. 12. We have 40 more minutes to go. We will be able to finish this chapter on relativity. Okay. And I need you to remember what you saw in relative motion. Okay, so remember what we did in relative motion during physics 6. Physics 06, right? So we consider two referentials, A and B. A is at rest with respect to us, and B is moving its constant velocity with respect to A. Because that's how we picture those two referentials, one moving with respect to the other. Velocity of B with respect to A. Okay, do you remember that? In physics 6, and we also have a notation, a mathematical notation that's very intuitive. Okay, in addition to those two referentials, we also have a point P somewhere in space, also moving with respect to the other two referentials. And then I'm going to illustrate the point P right in here. It's moving with respect to the other two referentials. This point can be located either with respect to referential A or B. Okay? Accordingly, we have the vector position of P with respect to A, which is equal R of P with respect to A, PA. And I'm going to illustrate that as well. I'm just refreshing, right, what you saw in relative motion in physics 6. So here we go. Vector position of P with respect to referential A goes from the origin of A to point P. And vector position of point P with respect to referential B goes from the origin of B to point P. And then we have this other vector position here. That is the vector position of referential B with respect to A, which is the vector that connects the origin of A to the origin of B. Okay. And now we're going to write down in terms of vector, in vector format, what you see right here. Okay. According to the above figure, we have the following relation for the position vector of point P. Position vector of point P with respect to A is position vector of referential B with respect to A, position vector of point P with respect to B. And I am going to rearrange, because by rearranging, we are going to have a very intuitive way of memorizing this relation that you see right in here. Okay, that's the equation that synthesizes relative motion. Okay, so here you go. Vector position of point P here on the left side. We have vector position of point P here on the left side as well, on the right side as well. Vector position of point P with respect to A. We also have another one that contains A here. And on the top of that, B doesn't appear in the left side, right? But it must appear on the right side if you want to convert from a referential in B to a referential in A. And look where B appears. B appears as the last term of the first vector and as the first term of the second vector. Can you remember that? PA, P here, A here, right? With respect to B, B doesn't appear, but the B is sandwiched between those two vector positions. Okay? And we can use the same reasoning to get other types of relative position, right? Here you go. We got the relative position of P with respect to A, but we also can get the relative position of P with respect to B, referential B. Here you go. We preserve P here at the beginning, we preserve B here at the end. Suppose that we have the position of point P with respect to referential A, and I want to convert it with the position of point P with respect to referential B, right? So Rp of B, P here in the first vector, B in the second vector, and sandwiched in between, we have the referential A. And then we have one more here. We can even come up with a referential of point P. Have you thought about that? We can even come up with referential of point P. Vector position of A with respect to B is equal to vector position of A with respect to P, right? A, B, B, and sandwiched between those two is the point P. And we have something similar for the relative velocity. That's the, here's relative position, right? The above are the equations for relative position. The above are the equations for relative position. The position. For relative velocity, we have something different. Something similar. The only thing that changes is the symbol. Okay? PA, PB, BA. PB, PA, AB, and so on. But let's not forget, these are the equations for the relative velocity, for the Newtonian relative velocity. Newtonian relative velocity. 20 more minutes to go, right? No, half hour to go. Half hour to go. These are the equations for Newtonian relative velocity. Which are an approximation to special relativity. Special relativity. Let's concentrate in this equation here, okay? We can choose any one of the three. Let's concentrate on this second one. Suppose we know the relative velocity of point P with respect to referential A, right? Then we have something like that. That for Newtonian mechanics, that's the equation for Newtonian mechanics. So the question is, how does this same equation should be here written in special relativity, right? I'm not going to derive that because it's required differential calculus, but it's not going to be difficult to memorize if you memorize this result here, mechanics. Okay, it's not going to be difficult. In special relativity, we are going to use this term here. This term here goes in the numerator, yes, but then there is a denominator term that we have to adjust that looks like the following. This is the correction term for relativity, right? Velocity of A with respect to B divided by C squared times velocity of P with respect to A. Okay? We can even put, I suggest that we put the VPA in front of, or even better, put it upstairs here, right? So we have the same mnemonic way of remembering the equation P here, right? I'm gonna put it in red color. And this other one, here you go. But it's not a summation, it's a multiplication, right? So if you memorize this one here, it shouldn't be difficult to memorize this term down here, right? So in relativity, velocities, they don't sum vectorially in a straightforward way. Okay, they do have a correction term. And the closer we get to relativistic speeds, the more important this term here becomes. And so here you go. We can do for VP sub A as well, VPA as well, right? So here you go. Newtonian mechanics, P sub A, right? So here you go, A here. But let's not forget that's going to be B, oops, and B. So here you go. We should copy down here for the relativistic term and replace A with B, right? A with B, right? Let's see if it's that right. Yeah, A is B. Okay, so that should be A here. Oops. Okay. VPB, VBA. Okay, just like before, if I, 'cause VAB much less than C, and VPA much less than C, then the last equation returns to the original one in mechanics, right? Or and we can come up with an example so you understand. Okay, we're going to do an example for real life situation, and then another one for relativistic situation, okay? Consider velocity of point P with respect to referential A as being 15 meters per second. And suppose that we have a second referential in which we are measuring the velocity of the referential A with respect to B as being 8 meters per second. Find what's going to be VP of B. What's going to be the velocity of point P with respect to B. Point P can be like a seagull, can be an airplane, right? Referential A can be the ground. Referential B can be another airplane, a second airplane that's flying. Or maybe even a bicycle, right? At this speed here. Yeah, it should be a bicycle. Okay. Or like I said, in this case, A is the truck, right? B is the ground referential, and P is the ball that's being propelled. Another way of looking at that. Using the equation mechanics and using the relativistic equation. Let's see how those two results compare. Okay. Solution. Item A. Item A. Item A. Okay. So all you have to do, find VPB, right? You want VPB, so you should know, should memorize, right? Should be VPA plus VAB, like that. Okay. VPA is 50 meters per second. V of A with respect to B should be 8 meters per second. And then what we get? We get 23 meters per second. And by the way, along the x-axis, okay? Consider along the x-axis. Axis, and VAB also along the x-axis. X-axis. Find VP of B in two different ways. Item A, I gotta put the x-axis here, x hat. like that. We get 23 meters per second along the x-axis. Yeah, we go. Now let's do that using relativity. Item B. Let's see what we get. That's the let's see here. We want VP of A, right? So we want VP of A. We want a different equation. VP of A. Let's see here. Okay. Oh, I should put VP of A here. Yeah. Okay, that's the one. That's VP of A. VP of B. Okay, now we have it right. We gotta use this one here. I didn't change the notation, right? Okay, VP of B. VP of B. Oh, he wants VP of B. Wait a minute. Yeah, we're going to use, okay, so since he wants VP of B, we're going to use VP of B. Yeah, here you go. I don't need that down there. Okay. Here you go. That's the one. VP of A. Okay, yeah, we still have downstairs, right? We got a 1 minus V. VP of A. Oh, okay. V A of B divided by C squared. Like that. Oh gosh. What am I doing here? Yeah, I gotta put it here. Yeah. Now, you go. This one I already know that upstairs is gonna be 23 meters per second, right? Here should be VPA 15 meters per second. The other is 8 meters per second. And you already know this guy is a very large number. Is 300,000 kilometers. I'm back. Again, internet, right? I'm recording here. Let me share the screen. Okay. So we must multiply 15. Do we have a positive or negative here? Let's see here. Yeah, we have a positive. So why did I put negative here? Huh? So it's 3 times 10 to the 8, right? Meters per second. Meters per second and raised to the power of 2. I'm going to change this to the multiplying sign. Here. So the meters per second, let's see here. We get what? 23 meters per second upstairs. Here is going to be 120, right? 120. Yep. This meter per second square is going to cancel out this other meter per second square right in here. And look at the number, right? And we still have to square this guy. Should be 9 times 10 to the 16. So whatever value that you have right in here is going to be very small. It's not going to affect much your result. Okay, it's it's going to be on 10 to minus 14 range. 10 to minus 14 range. Okay, and that is for the case of Newtonian velocities. But what happens if we have relativistic velocities, right? Now we're going to do an actual example that involves relativity. So here you go. This is approximately, I can put that, it is approximately 23 meters per second. Like that. Now let's take a look at this other example. We have 10 more minutes to go. 8 more minutes to go. Now consider a point P moving with this speed, 80% of the speed of the light, with respect to referential A. Referential A with respect, velocity of referential A with respect to referential B is 50% of the velocity of the light. And they are all along the x direction, right? Okay, in this case, A is the truck, B is the ground referential, and P is the ball that's being propelled. Using the equations of mechanics and using the equations Newtonian mechanics, and using the relativistic equation. Compare them all. Compare both results, right? So here you go. Solution. Let's see how different they are. That's the relativistic case, you can see that you're getting superluminal speeds, okay? We have never observed an object undergoing superluminal speeds. Now, what about, here you go. Newtonian mechanics predicts a superluminal speed. What about using relativity? Using relativity, we have that correction term downstairs, and I'm going to copy it so I don't have to type from scratch, right? That is VP over B. Let's see. Fine, VP over B. Okay. VP over B. That's not the one. Okay, VP over B. That's the one I want. Five more minutes to go. Now we are going to have something different, right? Already know what this term is, right? Already know it is 1.3. And let's not forget too, right, that we must have x hat here. And (1.3) P8 P8 PA is 0.8 C, 0.8 C. VAB is 0.5 C, 0.5 C. And C squared in the denominator is going to cancel out. C squared. We're talking about 0.4. Hmm. Here you go. And now we are going to get a speed that's not superluminal. 1.3 divided by 1.4. 1.3 divided by 1.4 is 0.93. The speed of the light. You will never get, and compare this result with Newtonian mechanics, right? Completely off. Completely off, right? We're talking about 40% difference with respect to the actual speed. 90, let's see, 93. Let's see. 103, 113. Yeah, 40 to 50% difference. Okay. So we're done. We're done with relativity. Let's see if we have anything else here. What the? Let's go get the. We have 2 more minutes to go. Let me get organized here. Okay, yeah. Sections of the book covered so far. You go. Equivalence of mass and energy. We did that, right? mc squared. And relativistic addition of velocities. You cannot sum up the velocities like we did in relative motion, right? You have to apply that correction term for relativistic velocities. So we are done with chapter 28. Do you have any questions? One more minute to go. I'll be here until 1:50 for my office hours. If you want to hang out and ask me some questions, I'll be available. Otherwise, I see you on Wednesday for the exam on Wednesday, third exam. Okay, see you on Wednesday.
Thank you.
Welcome. Let me stop sharing my screen. And I gotta stop recording.